So I'll take you through a small tour of using the core imaging library for optimization-based reconstruction. So it's building really a lot on top of what Andrew was and also Chris presented just before. So that's great. Thanks for setting all that up. Just as a reminder, on the CIL part of the training course, last week we covered sort of basic operations of CIL, and reconstruction with filtered back projection. This week we will be talking about optimization-based reconstruction, and in CIL you will learn how to specify optimization problems and run algorithms to solve these problems, and you will have a go at experimenting with different types of regularization and data fidelities and constraints. Right. Okay, so I just wanted to start out by a quick recap of the filtered back projection method that we used last week. So filtered back projection is a great algorithm. It's really fast. So you just need a single back projection and some FFT, that's all. It's been used in CT forever. People are familiar with it. It's easy to understand and even implement. And basically, the reconstruction behavior is very well understood. Some of the challenges with it is that you need basically you need a parallel beam geometry. You need sort of the standard geometry. And if you don't have that, then you need to work with a different variant of FBP for that particular geometry. Also, you need a decent quality data set. You need fairly many projections, and you need them to be of a decent quality, so not too noisy. If you don't have that, then FBP will not give a good reconstruction. Also, it's not possible to incorporate any sort of prior information that you may have about your about your image, such as we saw with the SIRF algorithm. You can say, I don't like negative pixels. Please, can I just have positive or zero valued pixels? We can't do anything like that with FBP. Now, if we turn to iterative reconstruction methods, this is a class of methods where you can sometimes, and I say sometimes, overcome these challenges. You can sometimes get a better image out than you can with FBP. Not always, and also it comes at the price of higher computational cost. Okay, so as we just saw before, typically we look at this regularized type problem, and here I've picked the Tikhonov problem. I tend to use U as my unknown image instead of X, so mostly these slides will have a U instead of the X as we saw before. So we tend to have a data fidelity term, which is measuring the fit to the data. And we have then another term, which is our regularizer over here. And in the Tikhonov formulation, we have a squared 2 norm over here. So U is the unknown image that we are looking to find, and alpha, or sometimes we put lambda or beta. This is our regularization parameter that governs the trade-off between these two terms here. And then we use our favorite algorithm that's suitable for the problem at hand, and we get a minimizer out, and that's our reconstructed image. So it's always going to be a balance between fitting the data and penalizing large values of whatever we put in here. And in the Tikhonov problem, which is something you will have a look at in one or more of the exercises in the CT branch, you can look at L being just the identity operator, so basically just looking at forcing large values of pixels to be controlled, to be smaller, which is good for just handling large noise values that may come into the image. More typically, we look at, I think this was also what Andrew mentioned, different type of difference operators. So typically we take gradients, spatial gradients across the image, horizontal and vertical differences, and this is good for making neighboring pixels similar, and also it has a smoothing effect on the image. And one thing that's important to note is that there's no one best choice of regularizer. What works well sometimes may not work well on other cases. It's all down to what kind of image type, what kind of features you expect in your image, and what kind of noise you've got. So that's important to keep in mind. One particular kind of regularization that's been used quite extensively is what's called total variation, and I'm sure many of you are familiar with it. So what total variation is suited for is generally homogeneous regions with sharp boundaries. So if you've got that, and we often have cases like that in CT, TV might be a suitable type of regularization method. Okay. And it's got the same form as I showed before. Here, apparently, I used a lambda for the regularization parameter. Apologies for that. But it's the same. We have a data fidelity, and then we've got, in this case, the TV regularizer over here. And just to show an example of what TV can do, normally, if we have, so this is a three-dimensional physical head phantom that's been scanned in a medical CT scanner. And if you use a full set of projection and the standard back projection type method for cone beam, you might get an image that looks something like this. So a cross section of the head, and I think these are little simulated tumors you've got here. Now, if you throw away most of the data, go over to the left here and just use 1/10 of the data, you basically get nothing but streaks. You just get lots of noise and lots of streaks, and you don't see the features you're looking for. Whereas if you switch to TV, again, using just 1/10 of the projections, then you get not a perfect image. You see there are some artifacts in different places, but if you're just looking to recover and quantify these features in here, you do a decent job by using TV, because this kind of image fits the underlying assumption for TV, namely that we have fairly uniform homogeneous regions with separated by sharp boundaries. And as Andrew mentioned, this is a kind of sparsity regularization. So in this case, we look at enforcing a sparse structure on the gradient image. Okay, so another thing we need to handle when we do regularized reconstruction is to decide which parameter, which regularization parameter do we like the best. So we can do different things, and a simple thing to do is basically run a sweep through different values. So if you put a large value, what that will give you is it'll put a large penalty of any sort of variation in the image. And that will essentially force all variations to be very small. And in the limit, you will get essentially a constant image, which we see is happening over here. On the other hand, if you use a very small value, it's like saying, basically ignore the regularization and just do least squares. And if we've got noisy data, typically least squares will give us a fairly noisy reconstruction, which is why we want to use regularization in the first place. So here's a very small value, and you see you get something very noisy. It's meant to just be a disk, a yellow disk on a blue background here. And then we have to pick something in between. And in this case, it happens that about 0.03 will give us a decent compromise between reducing the noise and also not getting a constant image. Right. So TV, and again, this is something that Andrew touched upon a little bit. It basically measures the variation of an image in a particular sense. And what it does is it looks at the gradient magnitude image, if you like, takes the size of that. So if we've got images from before here, so this is kind of the underlying image we're looking for. And we had the very noisy one over here and the very over-regularized, very smooth one over here. We compute the gradient magnitude image. So that's basically taking in each pixel, we look at the left, the horizontal difference and the vertical difference. And we square those and we sum those and take the square root of that. So it's the magnitude of the gradient in each pixel. We see we get something like this down here, and everywhere where it's constant, well, the difference is a 0, so TV becomes 0. So it's only basically at the edge we get a contribution, and then TV essentially sums all those contributions. And we see if we've got the image up here, we get apparently for this case 183 as the value for TV, whereas over here we get lots of zeros as well, and we basically get very small values because it's fairly constant. So this has a smaller TV, so TV tends to favor this kind of image, whereas this image over here, we see we get lots of non-zero contributions everywhere because we've got lots of noise, so the differences are not 0. And that means we get a very large TV over here. So this means that TV will not like this image. It will tend to help us get images that don't look like this, but look more like that. And then, of course, we have the trade-off where we also want to fit the data so that we don't end up with two constant images like this. Right, and the TV has been used quite a lot in tomography or other kinds of or variants of TV, particularly for cases where we've got few projections. So unfortunately, TV, and it is not so easy to optimize. The thing is, and this is really a key property of TV, it's not a smooth problem. It's not a differentiable function. And this is really due to the square root we've got in here. So normally when we do thick enough, we don't have the square root. So we've got everything squared here. So it's a nice parabola type of problem we're looking at. But when we do TV, we couple basically the X and Y horizontal and vertical directions by putting them underneath the square root together. And this means, unfortunately, that our objective function gets a kind of kink here. And that means it's not differentiable, and it means, unfortunately, we cannot use the nice gradient descent type methods for smooth optimization that we like to use. So the first approach is to say, okay, I can't solve this, but how about I just modify my problem slightly? So I add a small parameter underneath here, and this actually has the effect of turning the problem into, I think it's the green curve here. So the problem, you get rid of the kink here and you get a nice smooth function, and then you can minimize it using normal gradient descent type methods. Unfortunately, this is an approximation. It means that we will lose some of the nice benefits of TV, the edge preserving behavior. We may see some smoothing effects depending on how large a delta we pick here. So there's a trade-off in choosing this. Unfortunately, the smaller we pick the delta to be, which gives us a close approximation to the real TV, it also means it'll be harder to solve with gradient. It'll be slower for the gradient methods to solve it. But it's fine, and we can do this in CIL. It's often working quite well. Now, the other thing that we can do is we can use methods for non-smooth optimization. And here I'm just going to talk about one particular method, one of the simpler ones. We provide other ones in CIL as well. So for nonlinear, for non-smooth problems, we look typically at problems of a particular form and then derive algorithms that are suitable for this form. So in this case, we look at a problem where we've got an F term here, which is a normal smooth, so that differentiable function, so we can take gradients and so on. And then we've got another term over here, which is possibly non-smooth. We can't expect to be able to take gradients of G. And then a scalar here, which is typically our regularization parameter. Now the FISTA algorithm, which is the fast iterative shrinkage thresholding algorithm. Well, it takes a number of things in. You need what's called the Lipschitz constant of the F term, and you need to specify how many iterations to run. But other than that, it's not so different from gradient descent. In fact, we see that as the first step here. On the F part, we do a gradient step, and we do a step size with 1 over L, and then from this Y here. Now, the difference is that, as I mentioned, we can't do the gradient of G, but so what we need instead is we need to be able to take what's called the proximal mapping or proximal operator of G. And this is something we can compute from many functions. So it's a bit like taking the gradient, but it's not quite gradient because we can't take gradients of G. So we do that here for G, and then for FISTA, which is a faster version of what's called ISTA, we have a certain step size choice here, which help us to be a little bit faster. And this is described in this paper by Beckett et al. From 2009. Now this proximal thing, it's defined as another optimization problem, another minimization problem. So if you want to evaluate the proximal mapping of G for a particular image here called V, you need to find the minimize of this problem here. So we have some U, that you have the G of U, and then you have this quadratic here of U minus V, and you need to find the U that minimizes this, and this U will be the result of the proximal operator, and that's the thing you need to use in your FISTA algorithm. So basically, this means that FISTA is useful whenever we can do this easily. So when we have the proximal mapping available in a closed form, analytical expression, we do have that for many useful functions. That's great. We can use FISTA easily, or alternatively, if we can efficiently compute numerically this proximal mapping. So some examples, and these are ones that you will work with in the first notebook of this week. If we have the G function basically specify a constraint, so for example, we could have non-negativity specified as a constraint, then the proximal mapping simply amounts to doing a projection onto the non-negative numbers. And similarly, we can do sparsity type regularization by having a L1 norm as our G, and then the proximal mapping is what's called soft thresholding. So that's something you can do. And for TV, it's not quite as simple, but we do have numerical methods that can help us evaluate the proximal mapping quite efficiently, and that's you can then stick in the FISTA algorithm, and then you're good to go. And so I recommend this big paper here about proximal algorithms that talk a lot about different proximal, the proximal mapping and different algorithms that use it for nonlinear, non-smooth optimization. So in CIL, the good news is that basically you don't need to worry about much of this. You don't need to worry about Lipschitz constants or proximal mappings if you don't want to, because CIL handles all of that for you. So we provide in the optimization module, we provide different optimization algorithms that work for different types of problems. We provide a range of different functions that you can use to build your own optimization problems. And we provide a number of different operators, linear operators that you also need, like the system matrices and so on. And I think I won't go through the details of this, but I think the slides are being shared on the website or HackMD, so it's just to give you an overview of what's available. So we have different inverse problems, blurring operators, and gradient operators, basically building blocks that you need to piece together different kinds of regularizers. And also we've got projection operators from the Astra and Tegra toolbox down here. All are available as CIL linear operators. Then we've got different functions that you need to build your optimization problems, some building blocks here, and then various Kullback-Leibler, L1 norm, and L2 norm squared, these squares. So some of these are good for data fidelities, and some of them are more of the regularizer type. And we've got a number of algorithms as well, CTLS and SIRF, sort of the traditional iterative methods, the gradient descent method for smooth type optimization, and then for non-smooth problems we've got the FISTA algorithm that I mentioned, and other ones. And I think PDHG also plays a key role in the exercises this week. There's also one on SPDHG, which is a stochastic version of PDHG, which is faster. Right, so here's the slide again I showed last week with some resources. There's the main website where you can find everything, and then there's the documentation. And I updated the links here because these two papers are out now, so they will be available open access at these links here from the Royal Society A transaction. And finally, I just wanted to do a bit of shameless self-promotion here, because actually we have a book coming out next month. There's a book on computed tomography and algorithms inside and just enough theory, so covering many aspects about different iterative reconstruction methods, including proximal type methods. You see the SciEM people chose lots of prox stuff to put on the front page here. So next week it'll be available, and you can find it at this link here. Okay, so any questions at this point?
Yeah, Jakob, I got a question.
Mm-hmm.
So in all your slides, you always use the L squared L2 norm as the data fidelity term.
Mm-hmm.
But I mean, I guess in real life, the noise distribution of measured CT data is not purely Gaussian, right? So it's pretty complicated, and especially if you apply a log transform to the data. So are there are people using other data fidelity terms to basically better describe the noise structure of the acquired CT data?
Yeah. So great question. Many people use actually just the simple 2 norm like that. We also provide, which is I think more often used, this weighted L2 norm where you can specify weights that take into account the statistics of your data. So this will give you like the penalized weighted least squares population, or you can even go all the way and use the Colbert-Leibler for your data fidelity if you want to. But you're right. In my examples, I always used just the least squares. Any other questions? Or I'm going to share the notebook that I wanted to talk a little bit about, showing some of the SIL ways of doing what I just talked about. Let's see. Right. Okay. So if we for this week, we've got the week 2 folder on the STFC cloud with 5 different notebooks. Again, we've got an additional collection of resources. It's essentially the same resources, but the exercises that are suggested, additional things to do, are there are more things suggested here that you can have a go at. The one I wanted to show you here was the optimization with gradient descent and FISTA notebook that we've got here. I think it's pre-run, so hopefully it should be okay. So this is a case that was also used last week. It's this 3D parallel beam synchrotron dataset of a steel wire. It was used in notebook number 3, the pre-processing notebook from last week. So what I do here is basically reproduce the steps that we needed to load in the data and a pre-process it a little bit and do a basic FBP reconstruction. And then I define a custom display function just so that I can plot all of my reconstructions using in a consistent way. So it's called my show. So I show a 90-degree FBP reconstruction here, 2 different slices, and also I took a subsample data set with just 15 projections, which is the one I'm going to use more in this notebook. And we see, as expected, we get lots and lots of streak artifacts that show up here. Okay, so this is building quite closely on what Andrew talked about. We need to set up our linear inverse problem here. So we've got A, which is representing our forward operator, the system matrix, and the data's B here. So the first thing we do is and we did this last week as well, we set up the projection operator here. This is using Aspect, but could be Tigra as well, using the image geometry and the acquisition geometry that we loaded in with the data. Same things we needed for the FBP, and we specify here also we want to use the GPU. We just use the shorthand B to hold the 15 prediction data set. So the first problem we look at is what Andrew was also talking about, namely the least squares problem here. So we minimize the squared 2 norm, where the 2 norm is just the sum of all the elements squared. So this is our objective function. We want to minimize that. And as SIL, we've chosen an object-oriented setup. So to specify this objective function, or specify this function here, we have a class called least squares, and we specify, okay, I want a least squares object here with A and B, and then we get an F1, which is our least squares object. And that's basically all we need to do in this case. We need to specify also a starting point for our iterative algorithm. In this case, we say, well, I want an image, and so it's going to be of the same in the same space as the image geometry we use, and I just want to start with the 0 image. So I initialize that. Now this F1 thing we created here, it's a CIL function, and so we can evaluate that for a particular input. So we can say, well, for if I have an image, what's the function value of this image? So at the moment, we only have one image defined, the x naught, and so we can say, okay, what's the function value for x naught? And we put it into f, and we get this value out. So apparently, this is the value of our objective function for our starting point here. We can also evaluate gradient of our function. So we can say, well, for my function f1, what's the gradient evaluated at a particular point? Again, we just have the x naught. So we say, well, what does the gradient look like at x naught? And that's actually an image. So in this case, it's a 3-dimensional thing, and we can display that here. So apparently, our gradient looks like this. And I guess that means that you'll have all of this is 0. So if you take a gradient step, not much will happen up here. Whereas if you take with a gradient step, there's a big change here. You'll see a larger difference happening in this area. And I guess that's to be expected because this is already 0. Right. So to set up our algorithm, we want to use the gradient descent method here. We need to specify where we start, the initial point, what we are minimizing, the objective function. Then with gradient descent, you can either specify a fixed step size, which can sometimes be a good idea, or in our case, if you specify none, we will be using a backtracking line search. You can specify how many iterations at most you want to run and how often you want to see information on progress printed to the screen. So we do that here. We say a maximum 1,000 iterations. Specify our F1, which is what we wanted to minimize, and say, okay, every 10th iteration, let's have a look at how we are progressing. And then we set it up. We've got an algorithm instance here, and it hasn't done anything yet. It's just been set up. So we run it using the run command and say, I'm just going to run 300 iterations here and print basic information out. And here we go. So it prints every 10th iteration as we hope for. We see we are reducing the objective value here a lot in the beginning and then less as we get closer. And then at the end, we have in the algorithm object, we have solution available. And we can say, have a look at the solution. And apparently this is what it looks like. All right. So carrying on from here, we can now start looking at more complicated optimization problems. So for example, the ticket-off problem, we can do that in different ways. There's another notebook, I think it's the number 2 notebook, which talks more in detail about using a conjugate gradient type method for the ticket-off problem, which is oftentimes more efficient than gradient descent. But just to demonstrate gradient descent, I show what we can do here. We say again, I want my least squares function here. And now I want to build this sum function here, this function here. So first I need to build this term over here, and D is now a gradient operator. So we've got that in still. You can say I want the gradient operator. And I then want to have the square 2 norm of the result of the gradient operator. So that's basically composing this function with this operator. So in still, we have syntax to do that. So we can say, compose my operator and function together. We do that like this, and this is our F2. And then we say, well, F1 is this one plus alpha squared times F2. We can do that down here and define a new function object that holds both of them right here. So it's really near mathematical syntax, I think, as close as you can get. Okay, so now we do the same as before. We've got the F, and what we need to do is set up a gradient descent method. So we specify F again, and everything else as before, and then we can run 200 iterations in this case. And here we go. The solution looks something like this. So you can specify other optimization problems, just summing and scalar multiplying different function objects together. Right. So let's see. So here I have the same problem type as we looked at with the FISTA. Yes, so this is the FISTA stuff. So again, we have two terms, but now the G is not necessarily differentiable. So we need to do something else. And one of the things we can do is we can say, well, I want my G to be what's called an indicator function. So that specifies basically if my image is in the set I want it to be. Think of a set of non-negative values. Then this takes on the value 0, and if not, it takes on the value infinity. So this means it's still a convex problem. We can specify this kind of function in CIL. Call it an indicated box because you can specify lower and upper bounds. This we can then feed into FISTA. So we need F function, which we give here, and the G function. We need to specify where to start and how many iterations to run. And you see, we don't need to worry about this, the proximal mapping or the Lipschitz or anything. We just specify the functions because the functions hold the relevant methods to get the Lipschitz and the proximal and so on inside them. So the user doesn't need to worry about any of that. Then we can run FISTA, just like before. We run it 300 iterations, print some output. We see we are reducing the objective here. And in the end, we see we get a solution that looks like this. We see many of the streaks are gone because we have no negative values. So all of that have been removed, which also has a positive impact on the quality in here. It's not perfect, right? We still got lots of streaks, but it's helped for sure. The other thing we can do is we can look at the one norm, if we like. One norm sparsity time regularization. So we pick a regularizer that's just one norm. We have that available in CIL as the L1 norm, and we have a constant here, the regularization parameter. Again, we specify FISTA and run just like before, reduce the objective value. And in this case, we get something like this. And I don't know if this is a good reconstruction, but I think it makes sense what we get here because we've basically forced many of the values to be close to 0, which is what we do with sparsity type regularization. So basically, the largest values are kept here, and the rest of them are forced to 0. So just to show, this is sometimes useful, maybe not so much in this case. To do TV, we also have a function available in CIL. It's just called total variation. You can specify a regularization parameter here and run FISTA just like before. Total variation specifies the proximal mapping, everything you need. So you just run the FISTA. Again, we reduce the objective function. And we see in this case, we actually get a decent reconstruction out. We see our streaks are gone and the regions are fairly constant, just like we hoped. So TV is actually helping us quite a lot to handle view projection data here. We have also in CIL other algorithms than FISTA, for example, the primal dual hybrid gradient algorithm, the PDHG, which is useful for cases where FISTA, where this proximal mapping is not so simple and you need to decompose the problem a bit. So I just show here how you can solve the same problem using the PDHG algorithm. And you need to use these block functions to build block functions and block operators. But there's going to be a notebook that focuses more specifically on this. Here I just wanted to show you can set up the same objective function and you can solve it using this PDHG algorithm. And since it's the same objective function, the reconstructions should be the same, really. So in order to check that, we run quite a lot of iterations just to see at convergence whether they get to the same image. In practice, normally you wouldn't need to run this many iterations, but here it's just to get a very accurate solution. And we see the images look very, very alike. We got rid of the streaks again with TV. And the last thing I wanted to mention is we can also look at the objective values, the history of objective values as we, over the course of the algorithm run. So that's available as the objective field after we've run an algorithm. So we can, for the FISTA algorithm and the PDHG algorithm, we can extract these objectives and plot them. A nice thing about the PDHG algorithm is that it actually solves what's called a primal dual problem. So it's a long solving the main so-called primal problem. It's also solving an auxiliary problem, the dual problem, and it's giving us a dual objective as well. And the nice thing about that is that the difference between these two should go to 0 as we converge to the solution. So it's a measure of how well converged a solution we've got. We don't have that with FISTA, we just have the primal objective, but we can plot all of these. So for FISTA, we can see the decay of the function values as we go along. Here 100, this is log plot. After 100 iterations, we've made most of the progress, but we still make a little bit of progress. We also know that FISTA is actually not a descent method. Sometimes you can have, it can bounce up, and you'll sometimes see this sort of bouncing behavior, but overall there will be a reduction. PDHG, the orange one here, the primal objective, we see it reaches more or less the same value. It needs many more iterations, some thousands here I ran. They are a lot faster than the FISTA one because it's a simpler one. And we see the dual one is negative all along here, but finally here it becomes positive. And we can look at the difference, which is the red one here, the gap between those two different objective values. And that should go to 0 as we converge. So it nicely goes to 0 down here. And we can see that, okay, that means we are really solving the problem at this point. Once again, we don't normally need to run this many iterations, but it's nice to see that as we continue, we get to convergence. And I think that was what I wanted to say. Do we have time for questions? And do we have any questions?
Thanks, Jakob. Yeah, I guess so. I mean, don't see any in the chat, but I rejoined a bit later, and it looks like I can't see the history in the chat. So, any questions?
I don't see any.
I think they will come, right? Once people try these things.
Yeah. So once again, we've got, this was the first notebook. We've got also one that focuses more on the Tikhonov and also focuses on use of this block framework, the block operators, and so on, to get you familiar with that, which is something you need a little bit more when you look at the PDHG algorithm. And after that, there's the stochastic version of the PDHG. And the final one is Lego case in a laminography setup, where you can actually load in the Lego data set and look at the projections and do different kinds of instructions in a non-standard, so this tilted geometry. And also this shows you how to use a GPU accelerated version of the total variation from the regularization toolkit, which makes it a lot faster to do FISTA type TV reconstruction with CIL. So lots of different things to look at.